Guys, nice to see you. So, let us recall first a bit of our previous discussion. Uh, we remember that when we have some string and block system and they are oscillating, like in the block is oscillating in the case of absence of any drag force, it oscillates with so-called natural frequency, which is equal to square root of k divided by m, which is the strength coefficient divided by mass of the ball. So now, what we considered last time, we introduced drag force, and who will describe me what are the key changes of which this drag force induces in oscillations of such a system. So if there is some drag force, obviously there will be some dissipation of energy of the system. So we consider initially this case when we initially disturb the system and then let it oscillate by itself. So if there is some drag force, means that external force will perform some mechanical work. It will reduce mechanical energy of the oscillator, and eventually it will decay. The oscillation will decay. It will reside in equilibrium condition. So what is the what does it mean? So first of all, amplitude decays over time as exponential function. So very rapidly, amplitude goes to zero, means there is no oscillation anymore. And also we need to take into account that there is an effect of this drag force on the frequency. So the frequency of this oscillation will be constant. It will not change over time. However, it will not be equal to natural frequency. It will be modified because of additional drag force. And we also consider different extreme scenarios when frequency approaches. Oh, it actually was for the forced oscillation. So who will tell me what is forced oscillation? And when we do not want to let this oscillation to decay completely, we want to keep it going. So in that case, if we still have this drag force, we dissipate energy over time. So we need somehow to compensate this energy loss. So we provide, you're welcome, we provide certain periodic force which keeps driving this oscillation. And in this case, we end up after some equilibrium condition, already equilibration of all parameters, we end up with constant amplitude, which doesn't change over time because we compensate with periodic forces energy losses due to drag force. And also, the frequency of this oscillator will be defined by the frequency of the external force. So no matter what is the natural frequency of the oscillator, the main dominant factor which will define the resultant frequency of the oscillator will be the frequency of the external. So we also consider certain extreme conditions. So when frequency of external force approaches to zero, then it's just when we exert some constant force, we excite the system from equilibrium condition, we get some displacement, but then it does not result in any oscillations because it just moved from equilibrium conditions, the block, and then stuck in this position. Then we consider when frequency approaches to infinity, and that is the case when literally nothing is happening because we change frequency of this external force so fast that the system doesn't have time to respond. So in that case, It just does not even move from equilibrium condition, it just stays in equilibrium condition. And also, obviously, this resonant frequency when we achieve the maximum amplitude which is possible for given conditions. And what is condition of resonance? When frequency of the external force, we should specify frequency of the external periodic force coincides with the frequency, like natural frequency of the string block system. So now we continue further and start a new topic, which quite related to oscillations, but this topic will be about waves. So far we were talking about simple harmonic oscillators and how position along, let's say, axis x of this block, for instance, is changing over time. So at each moment of time, we wanted to know position of the block. That is full information we need to know about oscillator to describe it. Now imagine that we attach some string to such simple harmonic oscillator and let it oscillate. Obviously, this will transfer certain energy to the medium, which is the string, and we will create some wave which is traveling along the string. So our goal now will be to learn more about this wave and keep in mind that in this case when we have a wave, it's not enough to know the position of the block of the oscillator as a function of time. The thing is that we have oscillation of the element of the string. If we just consider small element of the string, it goes up and down. So we need to consider one additional dimension. It will be axis y. So we want to know how it changes along axis y as a function of position x along axis x and time. So that will be our wave function, which will be a goal of our today's discussion. So let us consider first a pulse. So pulse is a specific case of a wave. So when we have single disturbance, then this pulse is traveling along the medium. We cannot apply certain parameters with which we describe wave to pulse. For instance, we cannot apply wavelengths because pulse doesn't possess such term as a wavelength because we need to have some periodic function. Pulse is just one displacement. However, for instance, displacement and amplitude of this pulse, let's say amplitude is a shared parameter for both pulse and wave. So first we consider some pulse, and if we have a string which is attached to a wall, then we disturb this string from the edge. We create a pulse which will move with certain speed, certain velocity to the right, so from left to the right. As I mentioned before, in this case, we care about displacement along axis y of elements of this string, so it will be dy. And obviously you see that at different x, along like different coordinate x, we have different displacement. So this displacement will be a function of x. On top of that, if we consider also that it's moving, this pulse is moving from left to right, this displacement also will be a function of time. So we can write that this displacement delta y is a function of x and time. Let us introduce two main types of waves. So maybe you heard already that there are so-called transverse and longitudinal waves. Which types of waves we call transverse waves? When elements of the medium is displaced in the direction perpendicular to the direction of the wave traveling in this medium, that's the case when we have a transverse wave. There is possible a different scenario when an element of the medium, the displacement what it experienced, is in parallel direction to the direction of wave propagation. So, for instance, if we consider some string attached to the wall, and then we disturb some pulse in the string, we will have extended areas of the string, then compressed area, and again extended. So in this case, displacement of the elements of the string will happen in parallel to the direction of the pulse motion. So that is the so-called longitudinal wave. It has quite important practical meaning. So maybe someone knows what is a common approach, like most common and established approach to determine the position of epicenter, like exact location of the earthquake inside the Earth's crust. Maybe you heard about such seismological stations which record oscillations of the Earth's crust, this rocky material which forms the Earth's crust. And when something happens inside the Earth's crust, some disturbance, mechanical disturbance, then obviously it creates waves, like mechanical waves in this material. And taking into account that solid materials possess different mechanical properties for displacement and compression, longitudinal and transverse waves, which are generated because of some tectonical motion, they travel in the rocky material with different speeds. So if we have different sensors located in different positions with respect to epicenter, measure time intervals between transfer and longitudinal waves, longitudinal are faster, then we may determine with quite high accuracy where exactly the epicenter of the earthquake was located. There are also more complicated waves when we have a combination of both. For instance, waves on the surface of water. In that case, particles are moving, like if you consider some small volume of water, it performs certain circular motion. So there is some displacement perpendicular to the wave traveling, and also along the direction of wave travel. So in that case, we have a combination, but in general, we distinguish two main types of waves, which we have just described. Now, our goal will be to provide certain quantitative description of these pulses and waves. So we will provide information about wave form and wave function. We need to know and distinguish between these two terms. So waveform is kind of a snapshot of the wave. It is a function of displacement along axis y versus position along axis x. In this case, time is fixed, it's not a variable. However, if we want to know both position, like displacement as a function of position and time, then we already deal with wave function, and we will show how we go from equation which describes waveform to equation which describes wave function. So now let us consider such a pulse. X is x. This is our pulse. This is x is y. And assume that this is t equals 0. So we consider this pulse in some specific moment of time, which is t equals 0. Its shape can be described by so-called wave wave shape, and that is function of x at t equals 0, at time fixed. So that can be represented as some function of one variable x, because time doesn't change. Now let us pick up here some point P with coordinate x. And we assume that this pulse is moving from the left to the right along axis x with some velocity v. Now the question will be, if we consider this pulse, assuming that the shape of this pulse means this function doesn't change, so the shape of the pulse doesn't change, what will be the displacement of this point P after time interval t with respect to t equals 0? So this pulse is moving to the right. So let's draw here one more figure. It will be x. So we can continue here our axis y. And okay, let's assume that shapes are the same. But maybe I can make it a little bit better. Okay, so this is our coordinate x of point P. So this is our P. And this is the displacement y of this point P. So at time t equals 0 is displacement, let's consider it was 0. It was just in front of the peak. Now we want to know what will be the displacement of this point P after time interval t, when the shape of the pulse doesn't change. So in order to do this, what we can consider? After time interval t, this pulse will move certain distance. So if magnitude, like this amplitude value, was here at t equals 0, and this is amplitude value, so this interval here, this distance along axis x, is v times t, velocity of the pulse along axis x times time interval. So what we need to do in order to get to know what will be displacement of point P, we need to place here a distance, but to the left in opposite direction of motion of this peak, which is equal to v times t. So here will be some coordinate x minus v times t, and determine what was the displacement at this coordinate at time t equals 0. So when we determine this displacement, it will be some displacement y. That will be the same displacement of this point P after time interval t, because this pulse is moving to the right. So that means we can write that y as a function of x at moment of time t already, not 0, will be equal to y of x minus vt at time 0. So that is the way how we make the transition in this time interval t. And in this case, y as a function of x and t means a wave function already, can be represented as some function of x minus v times t. So now we have function which depends on two independent variables, x position and time t. V is considered as some coefficient there. So this is true when we have direction of traveling of this pulse from the left to the right along axis x. If, for instance, we have opposite direction, it goes in the opposite direction to axis x, we can write that y as a function of x and time will be equal to some function of x plus v times t. So this is where we can take into account the direction of pulse traveling. So that is the general description of how we go from the wave form function of one variable to wave function of two variables when we provide information on displacement of the element of this string as a function of position along axis x and time. So now when we already have this key understanding of waveform and wave function, let us consider some traveling wave. So we assume that we attached some simple harmonic oscillator to the end of the string. It vibrates, creates, like follows some oscillations, and generates certain wave in which is spreading along the string. So that will be some sinusoidal wave, and we will try to describe it. So let us consider such an example. We will have axis x, axis y. This is our sinusoidal wave. After some moment of time, so it moves with v velocity v along axis x. After some time from t equals 0, which is defined as t, this wave will travel along axis x, so it will look something like this. It will go here, say here, here. So this distance will be v times t. Between 2 points with the same phase of wave form at t equals 0, which is this black curve. Here t equals 0, and some time t, which corresponds to time interval t. So now let us define some parameters of the wave. So if we consider x and y, so here's our sinusoidal wave. The distance between 2 points along axis x, which are in the same phase, so means we can pick up, for instance, two amplitude uh, displacements, will be the wavelengths. So that is the parameter of the wave, which is wavelength, distance between 2 points in the same phase. So if we consider fixed position and time will be variable, and we will plot displacement of this element of the string at fixed x position over time. So here will be time, here will be displacement along axis y. We also have some sinusoidal curve here. And the time interval between two moments of time when the fixed or the element of the string at fixed coordinate x will possess the same phase will be given as period of this oscillation. The number of periods which can fit into unit of time will give us frequency of this wave. So frequency will be 1 over capital T. So now we have key parameters which describe the wave, and we want to get the equations for the waveform and wave function. Since it's sinusoidal wave, we can consider the wave function, the waveform, y as a function of x at t equals 0 as some amplitude a, capital A, times sinus a times x. And here this small a is a coefficient which we need to determine specifically to our wave which we consider. So let us get rid of this wavelength definition here, and we can pick up certain points of our interest in order to determine what this coefficient a should be, which stands next to x in the argument of sinus. So let us pick up first this point. So the coordinate of this point is 0, so it's beginning of axis x, and displacement y is also equal to 0. And this is at t equals to 0. So we can write that y of x equals 0 and time equals 0, so we have 0, 0, will be equal to a times sinus a times 0. And that is equal to 0. So sinus of 0 gives us 0, so everything is okay here. Then we need to determine another condition which will help us further to see what will be the value of this coefficient a. And let us pick up this point. So what will be the coordinate of this point? Lambda over 2. So we have half of wavelengths. This will be the distance between 0 and like first minimum and second minimum. So now what we see, x will be lambda over 2, but y is still 0 here, the displacement. So we can write that y at x, already here we write lambda over 2 at time t equals 0, so we just put 0 here. It's the same waveform. It gives us amplitude a times sinus this coefficient, unknown coefficient a times lambda over 2. And that is equal to 0 because we see that for this point, we also have displacement equal to 0. So assuming that a is not equal to 0, so a is not equal to 0, what this argument should be equal to? 2 pi. So there is only two options. Either we have 0 or pi. So a is not equal to 0, and x in this case also not equal to 0, then this should be equal to pi. A times lambda over 2 is equal to pi. And from here, we determine the value of our coefficient. So a will be equal to 2 pi over lambda. So now we can write the expression for the waveform of this sinusoidal wave. So let us write it here. Y as a function of x at t equals 0 will be magnitude, like amplitude value a times sinus 2 pi over lambda times x. So we have the expression for the waveform, and now if we assume that this wave is traveling to the right with some velocity v, we can make a transition from waveform to the wave function. We remember for wave which moves to the right, we need to subtract from position. In order to provide time dependence, we need to subtract from coordinate x product v times t. So in this case, we can write that y as a function of x and time should be equal to a times sinus 2 pi over lambda, and here v minus v times t, x minus v times t. So that is already the waveform, and we can use it, so it's okay. It's just this form is not very practical, and we will provide certain substitutions and modification in order to come to the final version, which is commonly used in practical applications. So let us first take a look here on this velocity. So what is like speed? V is equal to delta x over delta t. We know that during time interval, which is equal to the period of the wave, this wave travels certain distance. What distance is that? Wavelengths, exactly. So we can write here lambda divided by t. We know both numerator and denominator. Or in other form, we can write that it's equal to frequency times lambda, because 1 over t gives us frequency. So now let us take this ratio and substitute it here instead of velocity. So we write here y as a function of x and time will be equal to amplitude times sinus 2 pi over lambda x minus lambda over period times t. Let us take out, like factor out lambda from this parenthesis here, and we get y as a function of x and t equal to a times sinus 2 pi x over lambda minus t over period. So this is still not final form. We will make one more step further, but this form is very nice to show the periodic nature of this function, of this wave function, which describes sinusoidal wave. So looking here, we can make a statement about periodicity of this function with respect to position x and respect to time t. So let us see here. Let us consider only the argument in the parentheses. So x over lambda minus t over period can make a claim that this should be, if it's periodic, so it should be the same when we go to x plus lambda over lambda and minus t plus period over period. So if we go further, so what we have here, x over lambda plus unity minus t over period minus unity. We cancel out this unity, and indeed we get x over lambda minus t over period. So no matter how many lambda or periods we will add to time, like position and time, we will have the same result eventually. So we can write that if we fix time at t fixed, we will have the same outcome for x plus lambda, for x plus 2 lambda, so on for x plus n lambda. Also, if we fix position x, we will get for the same outcome for time t plus period t plus 2 periods and t plus n periods. So we show here the periodicity of this wave function for both independent variables, position and time. So now let us make one more step in order to come with the final form for the wave function. So here we need to introduce a new parameter, which is k, and that is 2 pi divided by lambda. So we call this wave number. So when we have this new parameter introduced, 2 pi over lambda, which is wave number, and we also remember that angular frequency is equal to what is equal if we want to express angular frequency in terms of period? 2 pi over period. So taking these two things into account, our previously derived wave function y as a function of x and t, which was written as a times sinus 2 pi x over lambda minus time over period now what we do here, we open the parentheses in the argument. So it will be a times sinus 2 pi over lambda times x minus 2 pi over period times time. And we see that this part is this new parameter which we introduced, wave number k, and this is angular frequency. So eventually we end up with the final form, which is commonly used in practical applications of the wave function for this considered sinusoidal wave. So that will be amplitude times sinus k times x minus omega times t. So that is our function, and of course that is true when we start from condition. So we consider this boundary condition t equals 0. So similar to the description of the simple harmonic oscillator, if we want to have a general form for this, we need to add here some phase shift, which will allow us to describe any case regardless at which position what is the displacement at x equals 0 and t equals 0. So we can write here the general case for displacement y as a function of position and time will be a times sinus k times x minus omega t plus some phase shift phi. So this is the general form for wave function of this sinusoidal wave, which we considered in this example. So we will continue working with this wave function in the future, determining some other features of the wave. However, at this point, our main goal was to come to this equation, which describes displacement of the elements of the string as a function of position along axis x and time t. So summarizing, we introduced like pulses and waves in this lecture, and one of the key features of waves, they do not transport material, they only transport energy. So we need to highlight here again that when we attach a simple harmonic oscillator to the edge of the string, we create a wave. Displacement of the elements of the wave happens only in the like periodic displacement only happens in the direction y, which is perpendicular to axis x. And that means that there is no motion of these elements of the string along axis x. So we transfer energy with the wave, but we don't transfer the medium, like elements of the medium in the same direction. And we introduce like two types of waves when we have displacement perpendicular to the direction of traveling of the wave, and when we have periodic displacement along traveling of the wave. So we have longitudinal and like traverse and longitudinal waves. So of course there are mixtures of them, and but two most common types. So it is necessary to remember and distinguish between wave form and wave function. So waveform is a snapshot of the wave. It's like a photo at given moment of time. We have a function of displacement only on position along axis x. So that uh, gives us only the form of the wave or form of the pulse. If we want to add this time dependence, because definitely it's a time dependent process, the propaggation of pulse or wave, we need to consider wave function. And in particular, we have shown how this general form of wave function looks like with introduction of new parameter wave number k, which is equal to 2 pi over lambda, the wavelength of the wave. On the example of a system, when we attach a simple harmonic oscillator to the end of the string and create a sinusoidal wave, which is traveling along this string. So with this, I thank you for your attention and hope to see you next lecture. Have a good evening.